Okay, so what's Data Modeler? It's, sort of depends on your point of view. It's the classic story of the blind man and the elephant, each looking at an elephant, and I just happened to have a rhino in my photo collection. So it was close enough. I mean, the approximation is very important in data analysis. So depending upon your need, is it the rapid data analysis, the ability to quickly turn around things? Do you care about generating human interpretable models and deriving the insight from those? Is variable selection the factor? I mean, in many multivariate systems, we've got lots and lots of variables, correlated, redundant. How do we choose from those what we need to do? There's also an aspect of if I'm going to use a model for prediction, and that's really the reason why you care about models. It's trustability. I mean, your conventional a single model is a big pile of trust me. So you say, how do I want to trust my predictions. I want to know it's good. When are my predictions suspect? And then the other aspect is once we get to this trustable models, then we actually have the foundation for what we call active design of experiments. In other words, to target my next collected data point to be the one with the maximum value and fidelity in terms of revealing the underlying mechanisms. The technology we use is symbolic regression. Basically, this means throwing into a vat your data, the variables, some operators, and constants, and just letting it percolate based on survival of the fittest to determine models that capture the behavior of the data. Now, what we want to do in this process is, what we care about for models. We want it to be simple and we want it to be accurate. So those are the sort of the primary drivers in this evolutionary process. And as a result, you will be hypothesizing many disparate models. You come through and reject them, refine them, and evolve simple models. If a variable is not important, it's going to be driven out. Let me go back here. So this is just an illustration. This is the Pareto front plot here showing the trade-off of complexity versus accuracy. What we have typically in a system is a sweet spot, this knee of the curve, which is where there's the best trade-off. And as you see, I mean, this little example, human interpretable models, we're condensing down into that sort of a space. So the process is an optimizer, not an optimizer, in the sense that we're, rather than being in the conventional analysis mode of hypothesis, test hypothesis, new hypothesis, cycling through, where the human is providing all of the sequence of hypotheses, we provide a framework. We say which variables should be included as a general rule, very loosely define what data is available, and then let the evolutionary process filter this down and isolate, build the models and select the variables. And the model development is infinite because there are an infinite number of models which will fit a finite data set exactly, right? And so if we want a loose approximation, there's an even more infinite number of models that are appropriate. But what we want to do is come sweeping in at the end and extract the insight out of the process. So the implications here is the transparency that we're looking at human interpretable models. So rather than a black box or a neural net or something like a random forest or a support vector machine, we're getting something that we could look at the equation or the expression describing the response behavior and say, well, that's funny, or what does that mean? We also have the ability to look at the models and say, are there building blocks that are successful in terms of good models? Like, and does that then derive insight? And we were doing some consulting work for a chemical company, and the difference between these two temperatures of the distillation column was very important for predicting the quality of the stuff that they're developing. So that was something that they were interested in. But in this evolutionary process, we're developing thousands and tens of thousands, maybe hundreds of thousands of models. And when we're all said and done, we're going to have a bunch that are approximately equivalent in terms of simplicity and accuracy. We can exploit that to build trustable models where we've got this, and these trustable models are going to agree where there's constrained by data, otherwise they wouldn't be good models. And they will disagree when either the underlying system changes or we ask it to extrapolate into a new region. So, and then when you have that ability for a trustable model, you can use it to target your data collection. So now if you imagine I'm designing a new material, I want to sample this data space, and then my next data collection, because if the experiments are expensive, is to go where the model is saying there's maximum divergence between in my trustable models. I'm going to go lock that point down and collect that information. Okay? So trustable models, I mean, this is the response plot explorer, but basically here you see the illustration of this collection of models. And so you have a prediction, but then we also see disagreement as we move away from the truth point. Here we've used an actual sample point is the green dot. As we move away from it into unsampled space, the agreement disappears, okay? So what over the last decade we've developed is a data modeler, which is an add-on package for Mathematica. 400 functions, fully documented. You don't use all of them during the course of a normal analysis, but they're there, exposed, using the notebook interface for the development of analyses, and 100% Mathematica. Now, and we've got clients, I mean, they're very happy with this that we sell. There is one problem with this notebook interface metaphor that we have in Mathematica, and that is Shift-Enter. Because it is amazing. I've had PhD electrical engineers that, Shift-Enter, they move the mouse over to the cell bracket and click on it. Then they hold the Shift key, and then they get the result, and they do that every time. And it's just sort of this touch typing, free-form control freak thing that you have with a notebook interface. There's a large chunk of the world that doesn't respond to that. So we need to figure out what we're going to do to eliminate Shift-Enter. So our approach is, I guess, a little less than a year ago, we started working on developing a GUI front end for the thing. And again, no shift, try to minimize the shift enters. You've got this problem if you've got a very, very powerful environment that's used for automotive analysis, chemical process industries, medical predictions, law. I mean, and of course, hedge funds. I mean, there's a wide variety in our user base. So it's very powerful, but how do you balance the power in the interface? So, on that note, let's go to. So here's the one shift enter that's still left in the system is to launch it there. So if I open a project, And this is, I'm going to be channeling my inner Steven here because I got this particular build about an hour ago. So we're going to, hopefully everything all hangs together. So I load, I've run this analysis, of course, before, and I'm going to select, we're going to model female literacy fraction, just as a toy problem. Okay, so first thing you need to do, so this is, we've been partnered, I should mention, Ariel Sepulveda of Prano Analytics has been developing the GUI with us. But the ability to just sort of explore the data. And you see we have a lot of missing records. First thing you want to do, of course, is to choose, what's my target variable? And then, is there a column in the data set, in this case, the countries of the world? Now, this thing is a combination of country data augmented with data I've scraped for gun usage, alcoholism, tobacco use, World Bank data that's all sort of integrated together. The raw data is 240 countries of the world and 231 columns. And then you can, then you define sub-variable sets. So let's explore the data. And here, this first view is the data summary table. And it's a quick overview of the data set. So we've categorized, how consistent is the data? What's its class? Is it a continuous variable? Does it look like it's categorical? What's its zero crossing behavior? Because that affects if I want to do, not quite implemented here, but implemented in the pro version, if you will, of Data Modeler. Analysis of, how do I want to do rescale of variables? But what we see here is this view, is if I'm analyzing literacy fraction, I've got, a lot of small countries in the world. So I may want to be normalizing inputs by population or some other factor. And also see that I've got 6 out of 7 continents covered. Now I can also come in here and of course plot the data. Now it's a little cluttered, so I'm going to come in and I'm going to turn off the ticks. And that gives me a little bit of a cleaner view. But I also say, okay, I'm looking more at the behavior relative to the female literacy. Let's sort it by that and do it a plot that way. Now I've got this graph. I can also capture this button here. Move it over. We'll capture it to our report notebook. So here we see reports that we can gather, and I'll check the box and I'll move it to the report, and I'll come back to the data exploration. The data completeness map, for many industrial systems, you can sort of count on the data being truly numeric. You do get some surprises that get uncovered where, somebody substituted minus 999 in for the missing data. So this is the sort of thing that the data summary table will capture and flag for you, because you'll get this big spike at that one value. But here we see that we've got a lot of missing data. Green is numeric. Yellow is red is non-numeric. We can look at the data completeness plot and see that South Sudan and Pitcairn Islands aren't very well populated in terms of their data records. And then we can look at the variables that we have in our data set. Bivariate plot doesn't make sense. I mean, you're looking at all pairwise combinations. I can go and I've got some models variables that I used, and this is just a pairwise scatter plot. Above the diagonal, we do the full range, and below it's the zooming in on the details with an automatic plot range, and of course, data histograms on the diagonal. Correlation chart of the correlations, but the opening going, we should look at all of them. And what we see here is we'll just put the bar origin on the bottom, and that will kill our 230 labels, 240 labels. So we're modeling literacy fraction. We're going to see that, or female literacy fraction and male literacy fraction are, of course, pretty highly coupled, as are other variables, okay? And the correlation matrix plot is similarly going to show, it takes a while a little bit, 10 seconds or so to calculate, but it's showing us the all pairwise correlations. Now the key here is we've gone through and we've got a lot of correlated variables to our targeted input, and we've also violating many of the assumptions. So blue is highly correlated, so we've got a lot of highly correlated inputs, okay? So now let's go look at generating models. And I have options here to control which functions I'm going to use. I can control which of the, how many variables I'm going to allow in my models, if there's a limit on the power levels. And also I can have, here I can have comments that I can attach to my each round of modeling. So in the interest of time, let's jump to the analysis phase. And let's retrieve interesting models from round 5. Okay. Oh, that's not quite what I want. Oh, cancel. Okay, thank you. All right, so now I'm going to go back to my model set of round 5. All right, just load that. All right, so this is all my models. So I've got 3,000 model or 2,000 models I've developed. I've done a bunch of 10-minute runs, quad-core processor running 4 of them at a time in parallel. I'm going to now go to my interesting round 5 models, load them, and show some of the analysis tools. So what we've done is we've had all these models. I can sort the models. I can say I want to restrict the number of variables to 3 variables, and say, how many have 3 variables, do those sorts of tests. But if I look at a model dimensionality table, that's taking the view of partitioning the data into its number of variables it's containing. And here we go. So what we see is that we have a lot of different paths to success for our models. So we have 4 variable models. I can have, country latitude, total, which is alcohol consumption in the country, various factors that are coming in. I can look at my variable presence chart, and this is what we've condensed down to, is the factors that have been important, that have emerged from the evolutionary process as drivers. I can also break my models up into their individual evolutionary searches. And that is useful because it can highlight mechanisms for variables that maybe aren't useful by themselves, but in conjunction with another variable in some particular expression form. They will occasionally be discovered, and at that point they'll be exploited by the evolutionary process and be highlighted. So here we see, for the most part, variables are heavily used, but cigarettes per capita is on average in 60% of the models at this stage of the modeling sequence, but it's, occasionally, one run at least it was up to 100%, and occasionally down to only being in 20% of the models. So we can also take that information and look at the meta-variable distributions. Now this is very important because I can see building blocks that I might want to exploit subsequently. So let's build, quick save, I'm out of time. And jump to our ensemble and look at an ensemble prediction plot. And this is a plot of my predictions of all these models. And what we see is the scatter of the data, so of the individual models. So we had, if you were paying attention in there, about a 80% R squared. So it's not an incredibly accurate model. You shouldn't expect that from a social science data set. And then this is supposed to be popping up the country name that would be associated with each of these outliers. I think I've run out of time, so I'm going to close out there and not show you some of the other features, but there's a struggle to have this much complexity be accessible. So, questions?
Maximum size of data that you're able to load in this?
It's under the hood, it's just Mathematica, so it's constrained. I'm going to assume that's the same as Data Modeler proper. And we've got users that are pushing 1 million records into it. We've done some stuff with 10,000 variables because you can handle this wide array type situation. So even though you have more columns than you have data records, you can still pull out information from that search process because of your value of simplicity. So you have a constraint of, I want each model to be supported by 4 or 5 data points, if you will. And you get this level of fidelity. So you can handle sort of the wide, and we've done it with some cancer prognostics data where 400 samples and 100 samples, 100 patients, and 400 proteins that have been involved. Okay, anything else?